This lesson is for Unit 1, Section 1, Matrix Operations, and this is Day 1. The first thing we need to talk about is a matrix. It is a rectangular array of numbers used to record data and solve systems of linear equations. So our first unit section, we're going to talk about the operations of them, and then the second part of our unit, we're going to talk about actually solving those systems. So matrices are usually drawn with these square brackets around them. And like it said, it's an array of numbers. So there are rows going across of numbers and then columns going up and down. It's read as m by n. The little x means by. So the first number they give is the number of rows, and the second number they give is the number of columns. So the dimensions are row by column. They do have some shorthand here. So if you notice, 1, 1 would stand for first row, first column. 1, 2 would be first row, second column, and so on. So that's what this little notation is here. So each of the elements in the row, like I said, can have a little subscript. They're also called entries. So if I'm looking at this picture here, and I had numbers in each of these spots, these are my 3 rows, right? Row 1, row 2, row 3. And these are my 2 columns, column 1, column 2. So the dimensions of this would be 3 by 2 because there were 3 rows and 2 columns. So for our first example, we want to know what is the order, or what are the dimensions of each matrix. So we're going to find the number of rows first and then the number of columns. So I have 1, 2 rows. So 2 by, I have 1, 2, 3 columns, so 3. So my order, or the dimensions of this matrix, are 2 by 3. All right, this one, for rows, we have 1, 2, 3, 4 by 1, 2. And then this one, rows, 1, 2, 3 by columns 1, 2, 3. All right. If matrices have the same order, which means they have the same dimensions, they can be added or subtracted by adding and subtracting the individual elements or entries. So notice these two matrices have the same dimensions. They're 3 by 1, right? 1, 2, 3 by 1, which means I can add them together by just adding the individual pieces. So 0 plus 1 is 1. 4 plus negative 9 is negative 5. 3 plus 8 is 11. So the answer should be the same dimensions as the original problems. This is a 3 by 1 matrix. In part B, we're subtracting. So we just have to remember, each time we compare elements or compare entries, we're going to make sure we subtract between. They're both 2 by 2 matrices, so my answer will also be a 2 by 2 matrix. So we're going to have 3 minus 2, and we get 1. 4 minus 1, we get 3. 9 minus negative 3, it's like 9 plus 3, so we get 12. And negative 5 minus 5, we get negative 10. So you can try these and pause it. I'm going to show the answers. All right, and there's your answers for those two. Scalar multiplication is when we multiply every entry or element in a matrix by a real number called the scalar. So it'll be written sometimes as this, with a number in front of the name of the matrix. They will name matrices sometimes to differentiate them for you. So Ka would be the value of K times every element in matrix A. So if in this example we're given the matrix A is really this 2 by 2 matrix, they want us to find 3.5A. So that means we're going to multiply every single term inside by 3.5. So I'm going to do 3.5 times 4, and I get 14. 3.5 times negative 6, I get negative 21. 3.5 times 12, I get 42. And 3.5 times 2, I get 7. So you go ahead and try this one. Find negative 2b given the 3 by 1 matrix B here. Pause it, and I'm going to show the answer. All right, and there's the answer for that one. So in our next example, this is probably the most applicable use of matrices. So here we have an example where a consumer advocacy group published the cost of Cheerios at 3 different stores. The prices were $3.97, $3.78, and $3.75 for stores A, B, and C, respectively. At those same stores, the store brand or generic cereal cost $2.64, $2.69, and $2.77. We're going to create a matrix with stores as rows and the Cheerio brand versus generic as the columns. So my 3 stores are going to be my rows: store A, store B, and store C. And then we're going to have the Cheerios brand versus generic. Just going to put gen. So for our matrix, it's going to be a 3 by 2 matrix. And I'm going to fill it in. So the 3 stores, A, B, and C, for the Cheerios price were $3.97, $3.78, and $3.75. For the generic, those 3 values at the same 3 stores, $2.64, $2.69, and $2.77. All right, so that's our matrix. For part B, find the cost of each cereal if there's a 6.25% sales tax. So if we called this whole matrix, let's give it a name. Let's call the whole matrix D, just because that's a letter I haven't used so far. So the matrix is D. So what we're really finding is what the cost of each cereal will be after we've added on 6.25%. So we know 6.25% is 0.0625. But that would just give us the tax if we found what 0.0625 is of each of these numbers. So in order to include the original, I'm going to multiply each one by 1.0625. So what we're really finding is 1.0625D. So that means every single number in here we're going to multiply by 1.0625. All right, and I'm going to round to the nearest hundredth, right, because we're talking about money. So if the third digit was 5 or greater, I'm rounding the second digit up. If it's 0 to 4, I'm going to keep it as the same. So 3.97 times 1.0625, I get 4.22. 3.78 times 1.0625, I get 4.02. 3.75 times the 1.0625, I get 3.98. 2.64 times the 1.0625, I get 2.81. 2.69 times 1.0625, I get 2.86. And then the 2.77 times 1.0625 is 2.94. Right? And that's the answer for part B. Some of the properties of matrix operations. All right, if A, B, and C are all different matrices with the same dimensions, and the lowercase letter k is our scalar, these are some things that we can do. So the associative property of addition, if I was adding A plus B in parentheses first and then adding C to that, that's the same as having added B plus C first and then adding A to it. Right? So the order we add together does not matter. And the commutative property, A plus B is the same as B plus A. Right? Doesn't matter which order we go. The multiplication or sum of different matrices by the scalar k also obeys the distributive property. So if I was doing k times the sum of A plus B, that's equivalent to k times A plus k times B, and the reverse is also true. If I had ka plus kb, I could really do k times the sum of A plus B, and the same thing for subtraction. So for this example, we want to find A plus 3 times B plus C. So this is our scalar, and I could either distribute or combine first and then multiply. They mean the same thing. So I'm going to do the addition first. So I'm going to just show B plus C first, because it's going to be a lot on my computer to try to write this all out. So I'm just going to focus on B plus C, right? It's this plus this. And I'll even show the whole thing 3 times. That's what we're really looking at. So doing just B plus C, 2 plus negative 1, negative 8 plus 4, negative 5 plus negative 3, and 6 plus 2. So that is our A plus C. So now it's this plus 3 times this. So now I'm going to do 3 times the B plus C, which means I'm going to multiply everything in here by 3. So now we have 3, negative 12, negative 24, and 24. And finally, it's A plus that. So now A plus 3 times B plus C. Normally, I would be writing out the full matrix each time, guys. So don't take my shortcut here as what you should do normally. So A plus 3 times B plus C. So that's 7 plus 3. 10 plus negative 12, 5 plus negative 24, 9 plus 24. Okay? And the last thing we're going to talk about, so we want to fill in the blank matrix to make a true equation. So negative 1 plus 0, we're just going to get negative 1 back, right? 3 plus 0, we're still going to get negative 3. And I'm going to keep going, and I get the same thing back each time, right? I get my original number back. So anytime we have a matrix with all zeros, what do you think we call that? We call that a zero matrix. And a zero matrix works the same way with addition and subtraction that the number 0 does in normal addition and subtraction. Right? If you add 0 to something, you get the original number back. So if you add a zero matrix to something, you get the original matrix back. And that is day 1 of matrix operations.